Okay, let's get rid of that. So today we are going to be talking about prime factorization and reducing or rationalizing denominators, reducing radicals, all sorts of good stuff. So when you're reducing fractions or simplifying radicals or rationalizing denominators, it's really important that you understand factorization. So what we want to do when we're dealing with prime factorization is, hold on just a second, we need to know what prime numbers are. Prime numbers are numbers which are divisible only by one in themselves. So when we're talking about prime factorization, what we're talking about is breaking down any non-prime number into its prime components. Okay? So, those are the first ones. So 8. 8 is 2 times 4. So what we want to do when we're breaking down something into its prime components, we want to sit there and we want to pull out the smallest prime number possible. So we want to start with 2. Once we get all the 2's out, we check for 3's. Once we get all the 3's out, we check for 5's, and so on and so forth. And what that allows us to do is make sure it gives us a process. It gives us the ability to sit there and go through prime factorization and make sure that when we get done with it, all we're left with is the prime numbers. If I start pulling out 4's or 8's or 16's or 25's, then that gives me multiple things to do in order to bring down the prime numbers. So let's look at 8. 8, we pull out a 2. 8 divided by 2 is 4. 4 is not a prime number. We can still divide that by 2. So now we have 2 times 2 times 2, and those are all prime numbers. So the prime factorization of 8 is 2 times 2 times 2. Okay? Prime factorization. 12. What we do is we pull out 2 times 6. 6, 2 times 3. 2 and 3, all prime numbers. 45. So 45, we can't divide by 2, so then we look at 3. 45 divided by 3 is 15. 15. Still can't divide by 2, and if we can't divide by 2 once, we can't divide by 2 ever. So 15, is there another 3 in there? Yeah, and it's 3 times 5. So the prime factorization of 45 would be 3 times 3 times 5. So let's look at something big, like 256. 256. 2 times 128. 128. 2 times 64. 64. 2 times 32. 32. 2 times 16. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. So we have 1, 2, 3, 4, 5, 6, 7, 8 2's here. Okay? So that's prime factorization. Okay? So this is a radical. This is the radicand. That's the number underneath there. So let's say we have the square root of 85. The square root of 85. So we're looking at this. Can't divide by 2. So we know we can pull 5 out. And that gives us 5 and 17. So when we're looking at square roots here, we need to realize that there is nothing there which will... So when we're having a square root, so this number right here, remember, is the index. So if it's a 3 or a 4, it's the third root or fourth root or whatever. So when we're looking at this, what we want to do is we want to sit there and go, okay, what sets are we looking for? So if it's a square root, we're looking for sets of 2. If it's a cubed root, we're looking for sets of 3. If it's a fourth root, we're looking for sets of 4. And so on and so forth. So 85 is 5 times 17. Both prime numbers, no sets, no pairs, can't do anything there. Let's look at 75. We can pull a 3 out, and that's 3 times 25. 25 is 5 times 5. So notice here we now have a pair of 5s. Okay? There are other ways to do this. So if you're doing this a different way or someone else teaches you a different way to do this, that's fine. I'm just going about it the most methodical way that I can to give you guys a very methodical way, and I know I just used that word twice, but a methodical way to work through these problems to make sure that you're getting the right answer. Okay, so this is 5 times 5. So because it's a square root and we have a pair of 5s underneath the radical, in the radicand, we can move 1 5 out. Because we can look at it like the square root of 3 times the square root of 25. So that's going to give us 5 radical 3. So because we had 2 inside, we move 1 out. Okay? So it's important to understand, I'm not sure what I did. Okay. So it's important to understand, and I just did squares up to 12, that squares and square roots are inverse operations, just like cubes and cube roots are inverse operations. So I'll do those over here. So like 2 cubed is 8, which means that the cubed root of 8 equals 2. 3 cubed is 27, which means that the cubed root of 27 equals 3. 5 cubed is 125, which means the cubed root of 125 equals 5. So it's important that when you see these numbers or these numbers pop up, in class there was that chart, the perfect cubes and perfect squares, but you guys should be used to seeing these numbers 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, so that when you see those, you can kind of shortcut it. See, if I look at 75 and I go 3 times 25, I go, oh, well, the square root of 25 is 5. I can just pull that 5 out right away. Okay, moving on. So square root of 3 times the square root of 6. So when we multiply, so notice that neither one of these can be reduced further. 3 is a prime number, and 6 is 3 times 2, both prime numbers. But when we multiply them, we get the square root of 18. Okay, so the square root of 18, now we have 2 times 9. 9 is 3 times 3. So now, all of a sudden, we have that pair of 3s. So we can take those pairs of 3s and move one of them outside, and we get 3 radical 2. And this is one that pops up a lot. Square root of 18 pops up a lot. Square root of 12 also pops up a lot. 12 is 4 times 3. Square root of 4 is 2. So the prime factorization of 12, we'd go 2 times 6, and that's 2 times 3. We have those 2 2's there. Move one of them outside. The 3 is left over inside. So that gives us 2 radical 3. Okay, what about cubed roots? So now, because it is no longer a square root, but a cubed root, we're not looking for sets of 2, we're looking for sets of 3. So 8 is 2 times 4, 4 is 2 times 2. We already did this, so 8 breaks down to 2 times 2 times 2. So that means that we have one set of 3 inside, so we can move 1 out. And then nothing's left over, so all we have is the cubed root of 8 is 2. So if we had the cubed root of 16, 16 is 2 times 8, 8 is 2 times 4, 4 is 2 times 2. So we have 4 2's. Well, because it's the cubed root, we take 3 of them, move 1 outside, and then what's ever left over inside, we multiply together, 2. So the cubed root of 16, we would simplify as 2 cubed root of 2. Let's take something like the square root of 32x to the 4th, 5y. Well, what we're going to do is we're going to start off with the square root of 32. We're going to break this down, and we're going to look at this as the square root of 32 times the square root of x to the 4th times the square root of y to the 5th. So 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. So we have 5 2's. So what we're doing is we're looking for pairs, okay? Looking for pairs of 2's. Here we have 2 pairs. So we move 2 2's outside, and 1 gets left over in the middle. Now with our x's, so 2 times 2 is 4. And with our x's, we have 4 x's. So we have 2 pairs of 2, and that takes care of all of them. The y's, we have 5. So just like the 2's, we have 2 pairs of 2's, and then 1 left over inside. So 2 times 2 is 4. On the outside, we have an x squared, a y squared. On the inside, we still have a 2 and a y, because they didn't have any friends. They couldn't go outside. So that would be our answer. 4x squared, y squared, times the square root of 2y. Okay, next we're going to talk about radicals, but I'm actually going to do that on a separate video. So, goodbye. See you shortly.